Okay, so let me proceed here. I've applied a force F, and I've asked you the question, what is the acceleration? Okay, now the answer here is pretty simple. What you would do, given that you've taken physics, mechanics, and so on, you would very quickly ask me what is the mass of the object, m, and I would very quickly tell you the mass of the object is m. And then you would very quickly respond that the acceleration is given by the force divided by the mass of the object. Gives you the acceleration. So that was pretty simple. So you ask me for m, I tell you what m is, you respond a equals f divided by m, and you are done. Okay, that was pretty simple. It wasn't hard at all. Now, why wasn't that hard? It wasn't hard because in trying to figure out the acceleration of the object, you just asked me for the mass m of the object. You ignored a whole bunch of other properties of the object. You ignored its shape, its temperature, its color, where did I apply the force, how it smelled, and so on and so forth. This kind of simplification where you took an object and you assumed that the object had a mass acting at a point and the force was applied at that point is called point mass discretization, okay, or point mass simplification. And by making the point mass simplification, you were able to tremendously simplify how you solved the problem, and in doing so, you were able to get the acceleration very, very quickly. Okay, so with this little piece of insight, let us go back to our light bulb example and see how we can find the current through the light bulb, through the filament, by an application of a voltage V, and somehow take inspiration from the point mass discretization that we did in physics. So let's stare at the bulb for a second here. Okay, in this bulb, we really don't care about exactly how the current flows inside the filament. We don't care about its temperature, its shape, its orientation. We just don't care about a lot of things as long as all I care about is what is the current through the bulb. So to do so, much like we did the point mass discretization, what we're going to do is we're going to replace the bulb with a discrete resistor. We're going to replace the bulb with a discrete resistor for the simple purpose of calculating the current, okay? And using this very simple model, this very simple simplification, I'm not going to be able to tell you what its temperature is or what its shape is and so on, but I will be able to tell you what its current is. So let's proceed with this simplification and continue down the easy path. So as I said, we'll replace the bulb with a discrete resistor for the purpose of computing the current. And so let me draw a little picture. So here's my representation for the battery. And what I'm going to do is here are my two points A and B representing the two terminals of the bulb. And I'm going to replace the bulb and model it as a resistor with resistance R. There's going to be some voltage V across the resistor, and my goal, as I said earlier, was to figure out the current I. So what I've done is I've replaced the bulb here with a resistor, where the resistor is serving as a model for the bulb. It's a discrete element called the resistor. And by doing so, now I can very quickly compute the current through the bulb using Ohm's law, as the current I is simply V divided by R. Now, wasn't that simple? Okay, show me where the differential equations are. They're all gone. Okay, by making an extremely simple model, by making the simplification and replacing all the properties of the bulb with the simple resistor with resistance R, I was able to compute the current I. Let me continue. And in EE, what we are going to be doing is we're going to be doing things a simple way. And in this particular situation, to find the current I through the bulb, I replaced the bulb with a resistor with resistance R, and I very quickly was able to find the current. So this is going to be a constant point that we make in 6002X, which is that in EECS, as engineers, we do things the easy way. In fact, this is true of all engineering, where in engineering, our goal is to build useful systems that help humanity, and our goal will be to try to do it in the simplest manner possible. Unlike science, where in science you have to learn what is, but in engineering, we're going to take the easiest path possible in order to build useful systems and possibly make as many simplifications as we want as long as we get to our goal. So in this particular situation with our resistance, R represents the only property of interest for us in terms of computing the current I for the filament of the bulb. So this is very much like the point mass simplification, where we replaced objects with their mass m in order to find the acceleration a equals f divided by m. So I really hope that you see this relationship between the simplifications we made in physics to the simplifications we make in EECS. And as we go on, I'm going to show you some really, really extraordinary results that we get by making some of these simplifications. So as I said, the R represents the key property of interest for the bulb and enables us to compute the current. What R has done is that it relates the voltage across the resistor to its current. Okay, so R relates the voltage and current related to the element. R relates the V and I for the element to each other by the expression I is given by V divided by R. So this relation, I equals V divided by R, is called the element VI relationship. So for various elements, I'm going to define a VI relationship for those elements that's going to capture the voltage and current relationships for each element that you will see in this course. So this lumped element R that we've created to replace the bulb for the purpose of computing the current through the bulb is a lumped element abstraction for the bulb. We've abstracted out all the properties of the bulb into this element R for the purpose of computing the current through the bulb. It's important for me to point out this word that you see here, abstraction. This is probably the single most common word that you will hear in an EECS curriculum. Okay, a large part of what we do in engineering is we build abstractions. We make things simple and represent them with some abstract properties. Okay, many of you have probably done computer programming, and in computer programming, you are very used to writing programs with several lines of code, and what you might do is if you have a function f with some arguments, then you might replace the properties and the actions of a bunch of lines of code with this abstract function f. So that's another example of abstraction where you are replacing f, where f replaces a set of lines of code that will perform the same function. So it's so much easier to use f. You simply call f. You can replace f. F can replace a set of lines of code. In the same manner, our element R will replace a large set of differential equations and properties that would characterize the bulb. So you will see this concept of abstraction again and again and again in all of electrical engineering and computer science as you do more and more courses in this area. And if there's one word that describes our entire field of EECS, it is this word abstraction. Okay, enough on abstraction. As you can see, I love the concept of abstraction, and let's very quickly summarize what we've seen so far. We've built lumped elements, and lumped elements are characterized by their VI relation. So for example, I could have a lumped element that looks like this, and I can define a voltage across a lumped element, and I can define a current through the lumped element. And in this case, when I define the voltage and the current going in through the positive terminal of the element, the power consumed by the element is given by VI. So remember this, you will see this again and again as well, that I take an element and I define a voltage V across the element, and I define a current going into the positive terminal of the element, and in that case, the power consumed by the element is going to be VI. Okay, I want you to be careful whenever you define power as whether the power is consumed by the element or power is supplied by the element. Okay, in this case, the power consumed by the element is VI. So to continue with the resistor, my resistor is a lumped element, and I can describe it with a voltage V and a current I, and I can also plot the values. So for the resistor, the VI relation is given by I equals V divided by R, where R is the resistance property of this resistor. So this element is characterized by its IV relation, I equals V divided by R. So one interesting computation you can make is how do you plot this element relationship on a IV curve? Then I show you a pair of axes here. So let me pause for a couple of seconds while you think about what this relationship might look like.